There's an invisible force out there, twisting the fabric of the universe in ways that defy everything we think we know. It's not gravity, not dark matter, not even light. It's something far more mysterious, something lurking in the shadows of cosmic giants, magnetic fields, but not just any magnetic fields. We're talking about forces so powerful they can rip atoms apart, warp space-time itself, and unleash energies beyond human comprehension. Imagine a magnet so strong, its pull could strip the iron from your blood from thousands of miles away. Sounds like science fiction. Out there in the cosmos, it's just another Tuesday. From the crushing depths of neutron stars to the chaotic edges of supermassive black holes, extreme magnetic fields are the universe's ultimate power players, silent architects of destruction and creation. They shape the fate of stars, bend jets of plasma light years long, and generate forces that make Earth's strongest magnets look like child's toys, and yet most of us never even think about them. That's about to change, because today we're diving into 30 mind-bending facts about these cosmic powerhouses, facts that will challenge everything you thought you knew about how the universe works. This isn't just a list, it's a journey into the extremes where physics as we know it starts to break down, where matter dances to the tune of invisible forces, and where the universe reveals its most violent, awe-inspiring secrets. By the end, you'll see the night sky differently. You'll understand why scientists obsess over these magnetic monsters, and you'll feel the sheer scale of their power. So buckle up, we're about to venture into the heart of magnetic madness, where the laws of nature get twisted and the universe shows off its most spectacular tricks. Ready? Let's go. Even among the universe's most extreme phenomena, few things match the raw, terrifying power of a magnetar. Picture a neutron star, a city-sized remnant of a supernova so dense that a single teaspoon of its material weighs 1 billion tons. Now take that unimaginable density and amplify its magnetic field to levels that defy human comprehension. We're not talking about refrigerator magnets or even hospital MRI machines here. A magnetar's magnetic field can reach a quadrillion times stronger than Earth's, making them the most intensely magnetic objects in the known universe. To put that into perspective, if a magnetar sat halfway between Earth and the Moon, its magnetic pull would erase the data from every credit card on the planet. These cosmic monsters are born in the chaos of a supernova explosion. When a massive star collapses under its own gravity, its core doesn't just condense into a neutron star, it turbocharges the original star's magnetic field, squeezing it tighter and tighter until it reaches unfathomable strength. The result, a celestial powerhouse that doesn't just bend the rules of physics, it shatters them. Magnetars don't sit quietly in space, they writhe, crack, and erupt with catastrophic violence. Starquakes' massive fractures in their ultra-dense crusts release pent-up energy in bursts of X-rays and gamma rays so intense they can be detected from billions of light years away. And then there are the flares. A single magnetar flare can unleash more energy in a fraction of a second than our sun emits in 100,000 years. The gamma rays from these outbursts don't just illuminate the cosmos, they rip through it with lethal force. If one happened within a few light years of Earth, it could strip away our ozone layer, triggering a mass extinction event. Yet, despite their destructive potential, magnetars also serve as natural laboratories, letting scientists test the laws of physics under conditions no experiment on Earth could ever replicate. They're a reminder that the universe isn't just stranger than we imagine. It's stranger than we can imagine, constantly pushing the limits of what we thought was possible. If magnetars are the universe's ultimate magnetic monsters, then SGR 180620 is their king. This cosmic beast, sitting about 50,000 light years away in the constellation Sagittarius, didn't just make waves in 2004, it unleashed a tsunami. On December 27th of that year, in just 1/10 of a second, This magnetar released a flare so powerful, it outshone every star in our galaxy combined. The energy it blasted into space was greater than what the Sun produces in 100,000 years. For perspective, that's like detonating 1 billion nuclear bombs simultaneously, except this wasn't destruction. It was nature flexing its muscles. What makes SGR 180620 so terrifying isn't just its outbursts, it's what's happening beneath the surface. Its magnetic field is so unimaginably strong, it actually warps the magnetar's own crust, twisting it like a pretzel under cosmic pressures. Think of it like bending a steel beam until it snaps, except here, the beam is a shell of ultra-dense matter tougher than anything on Earth. When these cracks form, they release pent-up energy in violent starquakes, rippling through space as blinding X-ray and gamma-ray flares. The 2004 event was so intense, it temporarily ionized Earth's upper atmosphere, disrupting radio communications and even affecting satellites. If this magnetar had been closer, say, within 10 light-years, that flare could have fried our planet's ozone layer, triggering a global catastrophe. Yet, for all its destructive potential, SGR 180620 is also a goldmine for scientists. It's like having a front-row seat to physics pushed to its breaking point, revealing how matter behaves under forces we can't recreate anywhere else. Here's the chilling part: we've barely scratched the surface. This magnetar's outbursts hint at even more extreme phenomena lurking in the cosmos. Some researchers speculate that certain mysterious fast radio bursts, those enigmatic, milliseconds-long blasts of radio waves from deep space, could be tied to magnetar activity. Every time SGR 180620 erupts, it's not just a spectacle. It's a message from the universe written in the language of magnetic fury. But if you thought magnetars were the only cosmic titans wielding magnetic chaos, wait until you meet the universe's ultimate particle accelerators, supermassive black holes. Take the monstrous black hole at the heart of Galaxy M87, famous for its first ever photographed shadow. This gravitational beast doesn't just devour matter. It spits out jets of plasma moving at nearly the speed of light, stretching over thousands of light-years into intergalactic space. And the secret behind these relativistic death beams: twisted magnetic fields so powerful they turn chaos into precision. Picture this: as matter spirals toward the black hole's event horizon, it doesn't just fall in smoothly. It gets caught in a cosmic whirlpool, swirling faster and faster like water draining from a bathtub. But here's where magnetism takes center stage. The black hole's rotation doesn't just drag space-time with it, it tangles the surrounding magnetic fields into a knot of unimaginable tension. These fields act like cosmic rubber bands stretched to their breaking point, and when they snap, they channel some of the infalling matter away from the black hole, launching it outward in jets thinner and more focused than a laser beam. The physics is mind-bending. Particles in these jets don't just coast, they're slingshotted to relativistic speeds by magnetic forces acting like an invisible railgun. Charged particles spiral along these twisted field lines, gaining energy with each loop until they're screaming through space at 99.9% the speed of light. The result, a beam so energetic, it glows across the entire electromagnetic spectrum from radio waves to gamma rays, visible across billions of light-years. What's even wilder, these jets stay razor straight for distances that dwarf entire galaxies. That's like firing a bullet from Earth and having it hit a target on Pluto without deviating by a single millimeter. Such precision defies intuition, but it's all thanks to the magnetic field's relentless grip, keeping the particles on track like an interstellar highway. Yet for all their power, these jets are more than just cosmic fireworks. They're sculptors of galactic evolution, pumping energy into their surroundings and shutting down star formation in entire galaxies. Some researchers even think they could seed the universe with the high-energy particles we detect as cosmic rays. So next time you gaze at a jet in an astronomical image, remember, you're not just looking at a streak of light. You're witnessing the signature of magnetic mastery, where gravity and magnetism dance in a partnership that shapes the cosmos itself. Earth's magnetic field might feel invisible in our daily lives, but it's working overtime to keep us safe from the universe's relentless fury. Picture a gentle bubble surrounding our planet, one that deflects deadly solar winds and cosmic rays like an umbrella in a storm. That's our magnetosphere, a protective shield generated by the churning of molten iron in Earth's core. While its strength averages just 50 microteslas, barely enough to nudge a compass needle, it's the only reason life thrives here. Without it, our atmosphere would be stripped away by solar radiation, leaving Earth as barren as Mars. But here's the humbling truth: our magnetic field is laughably weak compared to the cosmic heavyweights out there. Place Earth's magnetosphere next to a Magnetars, and the difference isn't just a matter of degree. It's like comparing a candle flame to a supernova. A Magnetar's magnetic field doesn't just deflect particles, it vaporizes them, wrenching electrons from atoms and reshaping matter into bizarre quantum states impossible to replicate on Earth. Even pulsars, the rapidly spinning corpses of dead stars, boast magnetic fields trillions of times stronger than ours, enough to accelerate particles to near light speed in milliseconds. The solar winds our magnetosphere battles. They're a gentle breeze compared to the hurricanes of plasma ejected by neutron stars. When our shield wobbles during a solar storm, we might see auroras or suffer satellite glitches. But if a Magnetar's flare grazed our solar system, no amount of shielding would save our technology, or possibly even our biology. Iron in our blood would align with its field like a compass needle gone haywire. Yet there's beauty in this fragility. Our modest magnetic field is a delicate balancing act, strong enough to protect, weak enough to allow life's chemistry to unfold. It's a reminder that cosmic extremes aren't just out there. They're the backdrop against which our existence hangs by a thread, governed by forces we're only beginning to comprehend. Pulsars take the raw power of neutron stars and turn it into one of nature's most precise cosmic clocks. These spinning stellar corpses pack the mass of a sun into a ball no wider than Manhattan, and their magnetic fields, trillions of times stronger than Earth's, transform them into celestial lighthouses. Every rotation, their beams of radiation sweep across space like a searchlight, flashing with such regularity you could set your watch by them. But don't let their rhythmic pulses fool you. Beneath that steady beat lies a maelstrom of magnetic violence. Take the Crab Pulsar, the heart of the Crab Nebula, a supernova remnant so famous, humans recorded its explosive birth nearly 1,000 years ago. This pulsar spins 30 times every second, whipping its magnetic field into a frenzy. At 100 million times the strength of Earth's, that field acts like a cosmic power plant, accelerating particles to nearly light speed. The result, a swirling storm of high-energy radiation that lights up the entire nebula around it. Electrons spiral along those twisted magnetic lines, emitting synchrotron radiation, a glow so intense the Crab Nebula shines brighter in X-rays than most stars do in visible light. What's truly staggering is the scale of energy at play. The pulsar's electromagnetic winds blast outward with enough force to expand the nebula at over 1,000 kilometers per second, sculpting filaments of gas into intricate glowing tendrils. It's like watching a cosmic sculptor work at light speed with magnetism as its chisel. And those lighthouse beams, they're not just pretty flashes. They're focused streams of radio waves, visible light, and even gamma rays, proof of a magnetic engine operating at the edge of physical possibility. Yet for all their fury, pulsars are also cosmic gifts to science. Their precise pulses let astronomers map the galaxy's magnetic fields, test Einstein's theory of relativity, and even hunt for gravitational waves. The Crab Pulsar, in particular, serves as a laboratory for extreme physics, proving that even in the graveyard of dead stars, magnetism writes the rules. Our sun may seem calm from Earth's cozy vantage point, but beneath that glowing surface rages a hidden storm of magnetic chaos. Every second, churning plasma, a seething ocean of superheated gas, acts like a cosmic generator, twisting and stretching magnetic fields with forces that dwarf anything humanity could create. These tangled fields don't just stay put, they snap like overstretched rubber bands, unleashing eruptions that make volcanic explosions look like firecrackers. Sunspots, they're just the visible scars of this battle, dark patches where magnetism stifles the sun's heat. Coronal loops, arcs of plasma trapped in magnetic cages, each one tall enough to swallow Earth whole. But the real fireworks come when these fields violently reconnect. Picture two colossal magnets crashing together, their lines of force breaking and realigning in a fraction of a second, a process called magnetic reconnection. The energy release is incomprehensible. A single solar flare can hurl out the equivalent of 1 billion hydrogen bombs, heating plasma to tens of millions of degrees and accelerating particles to near light speed. The most powerful flares, X-class, punch above even that, ejecting enough radiation to disrupt satellites, knock out power grids, and paint the skies with auroras as far south as the tropics. Here's the wild part. These solar tantrums are miniature versions of what magnetars do on a galactic scale. The physics is eerily similar: twisted magnetic fields storing unfathomable energy, then detonating in bursts that rewrite the rules of plasma behavior. The difference: scale. A magnetar's flare could vaporize a solar system, while the sun's might just fry our electronics. But both are reminders: magnetism isn't just some abstract force. It's the universe's ultimate conductor of chaos, turning serene cosmic objects into sudden, unpredictable tyrants. And the sun's magnetic mood swings aren't just spectacle, they're vital clues. Studying these eruptions helps scientists predict space weather, shielding astronauts and infrastructure from celestial tantrums. Every flicker of a solar flare is a message, a glimpse into how magnetic fury shapes not just our neighborhood but the galaxy beyond. While Earth's magnetic field quietly shields us from solar storms, Jupiter's is an absolute monster, a sprawling, chaotic empire of magnetism that could swallow our entire planet without breaking a sweat. Clocking in at 20,000 times stronger than Earth's, this magnetic behemoth stretches over 4 million miles into space, far enough to eclipse the sun if you were standing on Jupiter's cloud tops. But don't let its grandeur fool you. This isn't just a protective shield, it's a death trap. The radiation belts surrounding Jupiter, supercharged by its monstrous magnetic grip, are so intense they'd fry human DNA in seconds and cripple unprotected spacecraft like a lightning strike to a smartphone. The real twist: Jupiter's magnetic fury isn't just homegrown. It's fueled by its volcanic moon, Io, a world so geologically hyperactive, it makes Earth's volcanoes look like campfires. Every second, Io belches out a ton of sulfur dioxide gas and molten rock, painting its surface in neon yellows and fiery oranges. But the real spectacle happens when that material escapes into space, ionized by Jupiter's brutal radiation. These charged particles get snatched up by the planet's magnetic field, funneled into swirling currents that amplify Jupiter's radiation belts to unimaginable levels. It's like a cosmic generator running on volcanic exhaust. Here's where things get even wilder. The interaction between Io and Jupiter's magnetism creates permanent auroras, not just at the poles but circling the planet in glowing electric halos. These aren't the gentle northern lights we know. They're mega auroras pumping out terawatts of energy, hot enough to vaporize metal and visible across the solar system. Meanwhile, the radiation belts dubbed the Jovian death zone are churn with electrons moving at nearly light speed, creating a hazard so severe, NASA, a Juno probe, had to armor itself in titanium just to survive occasional dips into the chaos. Yet for all its violence, Jupiter's magnetic empire is a masterpiece of cosmic physics. It's a living laboratory for how planets interact with their moons, how magnetic fields shape space weather, and how radiation can both create and destroy. And lurking in that chaos might be answers to questions we haven't even thought to ask, like how exoplanets around distant stars could harness similar forces to shape their own destinies. One thing's certain, Jupiter doesn't just have a magnetic field, it reigns over one. White dwarfs are supposed to be the quiet retirees of the stellar world, cooling embers of dead stars, fading slowly into cosmic obscurity. But some of these stellar corpses refuse to go gently. Take GD356, a white dwarf that didn't just keep a souvenir from its explosive past, it weaponized it. This dense, Earth-sized remnant, packing half the Sun's mass into a sphere smaller than our planet, wields a magnetic field 100 million times stronger than Earth. That's not just a lingering whisper of magnetism, it's a scream from the grave, proof that even in death, stars can cling to their most violent traits. How does something so small become so magnetically ferocious? The secret lies in the white dwarf's birth. When a sun-like star dies, it doesn't go out with a supernova's bang. Instead, it sheds its outer layers, leaving behind a super-dense core, a white dwarf. But if the original star had a strong magnetic field, that field doesn't vanish. It gets squeezed, amplified, and fossilized into the core as the star collapses. Imagine taking a weak bar magnet and crushing it into the size of a sugar cube. Its magnetic field would skyrocket in intensity. That's exactly what happens here, except instead of a sugar cube, it's a celestial body with gravity so strong, a teaspoon of its material would weigh as much as an elephant. GD356 takes this to extremes. Its magnetic field isn't just strong, it's structured like a cosmic bullseye, with poles so intense they trap ionized gas in a perpetual dance. This creates eerie auroras on the white dwarf's surface, glowing not from starlight but from pure magnetic energy. And here's the kicker, these fields are so powerful, they can actually alter the quantum behavior of atoms in the white dwarf's crust, forcing electrons to move in bizarre, magnetically dictated paths. What's truly fascinating is how these magnetic white dwarfs challenge our understanding of stellar evolution. They're cosmic time capsules, preserving magnetic blueprints from their ancestors' blueprints that might reveal how magnetic fields shape stars across billions of years. Some researchers even speculate that a fraction of these magnetic monsters could one day detonate as supernova, their pent-up energy finally unleashed in a final, catastrophic farewell. For now, though, GD356 and its kind serve as a reminder. In the universe, even the quietest corners can hide the most shocking secrets. Fast radio bursts are the universe's most enigmatic screams, blasts of radio waves so intense they outshine entire galaxies for milliseconds before vanishing without a trace. For years, these cosmic flashes baffled astronomers, appearing random and fleeting. Then along came FRB 121102, the first repeating fast radio burst ever discovered. Unlike its one and done cousins, this one kept coming back, firing off radio pulses like a celestial Morse code from a galaxy 3 billion light-years away. And the more scientists studied it, the clearer the culprit became, an extreme magnetic environment, possibly a magnetar on steroids. Imagine a magnetar's magnetic field so twisted, it acts like a cosmic slingshot. As the field lines snap and reconnect, think of rubber bands stretched to their limit. They unleash torrents of energy capable of accelerating particles to near light speed. Now picture that same magnetar shrouded in a nebula of dense plasma, its magnetic tendrils weaving through the chaos like live wires in a storm. When those particles slam into the surrounding plasma, they emit a brilliant flash of radio waves, a fast radio burst. The repeating pattern, that's the magnetar's magnetic field winding up and snapping back over and over, like a ticking time bomb of cosmic proportions. What makes FRB 121102 even stranger is its home, a turbulent, star-forming region thick with magnetic turbulence. This isn't some quiet corner of the universe. It's a cosmic war zone where newborn stars and supernova remnants churn the magnetic fields into a frenzy. Some researchers speculate that the magnetar responsible might be a rare hybrid, caught in the act of devouring a companion star or tangled in the wreckage of its own explosive birth. Every time it erupts, it doesn't just send out a radio burst, it sends a coded message about the most extreme physics in the cosmos. Here's the real kicker: these bursts aren't just random noise. Their radio waves are polarized, twisted like a corkscrew as they travel through the Magnetar's insanely strong magnetic field. By studying this twist, astronomers can map the invisible forces at work, forces so powerful they warp the very fabric of space around them. It's like decoding the fingerprint of a cosmic monster, revealing secrets about magnetic fields we could never recreate in a lab. And with every new burst, the universe whispers another clue, pulling us deeper into the mystery of these magnetic maestros. Galaxies might look like glittering islands of stars, but their true skeleton isn't made of light, it's woven from invisible threads of magnetism. The Milky Way alone is laced with a sprawling network of magnetic filaments, some stretching tens of thousands of light years, their delicate tendrils guiding cosmic rays like interstellar highways. These fields might not rival the brutal strength of a magnetar, but their influence is just as profound. Imagine a spider's silk, fragile on its own, yet strong enough to shape the fate of everything that brushes against it. Take the Milky Way's spiral arms. Their iconic swirl isn't just gravity's handiwork. Magnetic fields act like cosmic sculptors, channeling clouds of gas and dust into dense ribbons where stars are born. Without these invisible forces, our galaxy's arms might unravel into chaos. Recent radio telescope observations reveal something even wilder. These galactic fields aren't static. They ripple and twist as if the Milky Way itself is breathing. When supernova explode or black holes belch jets, they send shockwaves through this magnetic web, realigning filaments like gusts of wind bending a field of wheat. But the real magic happens in the details. Cosmic rays, subatomic particles racing through space at near light speed, don't travel randomly. They surf along these magnetic highways, their paths curving gently like marbles rolling through a labyrinth. That's why when astronomers map cosmic rays, they aren't just tracing particles, they're indirectly charting the galaxy's hidden magnetic blueprint. Some researchers suspect these fields even protect star-forming regions, shielding fragile stellar nurseries from the galaxy's turbulent heart. Yet for all their quiet power, galactic magnetic fields hold mysteries we've barely begun to unravel. How do they maintain their structure across millions of years? Why do some galaxies, like Andromeda, show eerily organized magnetic patterns, while others resemble tangled balls of yarn? Each new observation peels back another layer, revealing a universe where magnetism isn't just a side effect, it's the silent architect of cosmic order. Magnetic reconnection might sound like a technical term, but it's the universe's ultimate power switch, a cosmic short circuit that turns invisible magnetic fury into bursts of light and radiation bright enough to outshine galaxies. Picture two magnetic field lines stretched taut like rubber bands loaded with pent-up energy. When they snap and reconnect, the energy release is catastrophic. It's the same physics that powers solar flares, magnetar outbursts, and even the shimmering curtains of Earth's auroras, just scaled to extremes that defy imagination. Take the sun's tantrums. A single X-class flare starts with magnetic loops rising from the solar surface, their field lines tangling into knots of tension. When these lines finally break and realign, the energy converts in milliseconds, heating plasma to tens of millions of degrees and launching charged particles at nearly the speed of light. The result, a flash brighter than 1 billion atomic bombs hurling radiation across the solar system. But here's the twist: that same process, scaled up a quadrillion times, is what makes magnetars so terrifying. Their crusts crack under magnetic strain, triggering reconnection events that fire gamma-ray flares capable of sterilizing planets light years away. the real magic lies in the efficiency. Magnetic reconnection doesn't just release energy, it funnels it with surgical precision. In a lab, we struggle to replicate even a fraction of this efficiency, yet in space, it's nature's favorite tool. Earth's magnetosphere uses it to funnel solar wind energy into dazzling auroras. Black holes leverage it to launch jets of plasma across galaxies. Even the Crab Nebula's pulsar wind, a hurricane of charged particles, relies on reconnection to accelerate electrons to near light speed, creating its iconic glow. What's wild is how universal this mechanism is. From the smallest solar flare to the most violent magnetar burst, the same fundamental physics is at work. It's a reminder that the universe, for all its complexity, loves to recycle its tricks, just with increasingly apocalyptic stakes. Neutron stars aren't just dense, they're armored in the toughest material the universe can forge. Their crusts, a crystalline lattice of iron nuclei packed so tightly they touch, are 100 billion times stronger than steel, yet even this cosmic armor has its limits. When a neutron star's magnetic field, already trillions of times stronger than Earth's, gets twisted beyond endurance, the crust doesn't bend, it breaks. These fractures, called starquakes, are unlike anything on Earth. Imagine an earthquake so violent, it splits a continent in half, then compress that energy into a crack no wider than a pencil and a fraction of a second long. That's the scale we're talking about. The moment a starquake rips through the crust, the neutron star's magnetic field whips like a snapped cable. Pent-up energy explodes outward, heating the surface to millions of degrees in milliseconds and blasting X-rays and gamma rays across the cosmos. In 2004, astronomers witnessed one such event on SGR 180620, a magnetar whose starquake released more energy than our Sun emits in a century. The blast was so bright, it bounced off the Moon and lit up Earth's upper atmosphere like a cosmic flashbulb. What makes these cracks even wilder is what they reveal about the star's interior. The vibrations from starquakes ripple through the neutron star like seismic waves, letting scientists listen to its structure. The data paints a surreal picture. Beneath the crust, protons and electrons are crushed into a quantum soup of superconducting fluids, while the core, possibly a hyperdense tangle of exotic particles, defies known physics. Every starquake is like peeling back another layer of this cosmic onion, exposing forces so extreme they rewrite the rules of matter itself. Yet for all their violence, starquakes are also cosmic clocks. Some magnetars, like a twisted version of Old Faithful, erupt in semi-regular bursts, their crusts fracturing under rhythmic magnetic stress. Each crack is a reminder, even in the cold depths of space, nothing sits still. The universe is alive with tension, bending and breaking under forces we're only beginning to measure. And every time a neutron star's crust snaps, it sends a message, written in gravity, magnetism, and light, about the raw power lurking beneath the surface of the cosmos. Long before the first stars flickered to life, the universe was a seething ocean of plasma, a place where magnetism didn't just exist, it ruled. In those primordial moments, some theories suggest magnetic fields weren't the subtle forces we know today. They were titanic, woven into the fabric of space itself, strong enough to twist the paths of particles and sculpt the earliest structures in existence. Imagine a cosmos where magnetism wasn't a side effect but a foundation, a hidden hand guiding the birth of everything we see. These hypermagnetic fields likely arose from the universe's most violent infancy, quantum fluctuations stretched to cosmic scales during inflation, or perhaps the turbulent churn of plasma in the first microseconds after the Big Bang. Unlike today's magnetic fields tied to stars or galaxies, these were primordial, baked into space-time like cosmic fingerprints, and their influence might have been profound. Some models suggest they nudged gas clouds into collapsing into the first protogalaxies, acting as invisible scaffolds for the universe's largest structures. Without them, galaxies like our Milky Way might have formed differently, or not at all. But did these fields vanish when the universe cooled? Not entirely. Astronomers now hunt for their ghostly remnants in the emptiest places imaginable: cosmic voids, those vast deserts between galaxy clusters. In these near-perfect vacuums where matter is so sparse it's practically a mirage, weak magnetic fields persist. They're whispers of that ancient fury, too faint to detect directly but hinted at by the way they polarize light from distant quasars. If confirmed, these relic fields would be the oldest magnets in existence, older than stars, older than atoms, a living memory of the universe's magnetic dawn. What's chilling is the scale of their longevity. Surviving 14 billion years of cosmic expansion, these fields would have witnessed the rise and fall of galaxies, the birth of black holes, the death of stars, all while retaining traces of their original strength. They're not just fossils, they're time capsules holding secrets about how the universe transitioned from a seething plasma to the structured cosmos we know today. And if we can decode their faint signals, we might finally understand magnetism's role in writing the universe's first and most dramatic chapter. Deep within the swirling chaos of a stellar nursery, a cosmic construction project is underway, and magnetism is the foreman. Take HL Tau, a toddler star just 1 million years old, nestled in a thick disk of gas and dust. To the untrained eye, it might look like a simple whirlpool of material waiting to collapse. But hidden beneath that chaos is an invisible scaffold of magnetic fields, guiding every step of this star's violent growth spurt. These fields don't just hover passively, they orchestrate, twisting the disk into a finely tuned delivery system for stellar fuel. Here's how the magic works. As the protostellar disk spins, ionized particles, atoms stripped of their electrons, get caught in the magnetic field's grip. Like beads on a wire, they spiral along these invisible lines toward the growing star, funneling gas and dust inward with eerie precision. Without this magnetic highway, the disk would fling material outward like a splash from a spinning carousel. Instead, the field acts as a cosmic brake, stealing angular momentum and redirecting it into controlled accretion. But the real marvel lies in the details. ALMA Observatory's radio images reveal dark gaps in HL Tau's disk, signs of planets carving their paths. And guess what's helping sculpt those gaps? The same magnetic fields that feed the star also nudge dust grains into clumps, seeding the birth of future worlds. It's a double act. Magnetism builds the star and the planets around it, like a baker kneading dough while sprinkles settle into place. The numbers are staggering. These protostellar fields can channel material at speeds topping 100 kilometers per second, enough to swallow an Earth's worth of mass every year. Yet for all that fury, the process is astonishingly precise. Simulations show magnetic fields creating accretion columns, narrow streams of matter plunging toward the star like water down a drain. Occasionally, these columns snap under the strain, triggering mini flares brighter than our sun. What's wild is how universal this blueprint seems. From HL Tau to Orion's fiery nurseries, young stars everywhere appear to rely on magnetic conveyor belts to grow. Even our own solar system likely formed under these invisible guidelines, meaning Earth and everything on it might owe its existence to magnetism's quiet choreography. It's humbling to think that the same force that holds fridge magnets in place also shaped the architecture of worlds. Some stellar duets in the cosmos aren't just beautiful, they're downright lethal. Take GRO J100857, a high-mass X-ray binary where a neutron star and its companion are locked in a gravitational tango with deadly consequences. The neutron star, a city-sized remnant packing more mass than our sun, doesn't just orbit its partner, it mercilessly strips gas from the larger star's surface, funneling it into columns of superheated plasma. But here's where things get bizarre. This isn't a chaotic free-for-all. The neutron star's magnetic field, a trillion times stronger than Earth's, acts like a cosmic traffic cop, forcing the stolen material into precise, spiraling pathways called accretion curtains. Picture a waterfall of star stuff, but instead of falling randomly, it's guided by invisible magnetic rails toward the neutron star's poles. As the gas accelerates to nearly light speed, friction heats it to hundreds of millions of degrees, igniting a constant storm of X-rays so intense they outshine the combined light of both stars. These aren't subtle glows, they're deadly laser beams slicing through space, detectable across thousands of light years. The curtains themselves are like twisted funnels of magnetized plasma, writhing under forces that would vaporize any known material in an instant. What makes JROJ 100857 so fascinating isn't just the violence, it's the precision. The neutron star's rotation and magnetic axis are misaligned, causing those X-ray beams to sweep across space like a lighthouse from hell. When Earth happens to lie in their path, we see periodic bursts of radiation, flashing with a rhythm so exact it rivals atomic clocks. Scientists have even caught this system mid-outburst, watching as the accretion rate suddenly spikes, turning the neutron star into an X-ray flamethrower for weeks at a time. But the real kicker, this deadly dance is temporary. Over millennia, the neutron star's magnetic field will gradually weaken, and those perfect accretion curtains will falter. The show will end not with a bang, but with the slow dimming of a cosmic predator that's finally run out of prey. Until then, JROJ 100857 remains a stark reminder. In the universe, even destruction can be breathtakingly elegant. At the crushing densities inside a magnetar's crust, matter doesn't just behave strangely, it surrenders entirely to the tyranny of magnetism. Here, atoms aren't the tidy spheres we know. Under magnetic fields a quadrillion times stronger than Earth's, electrons are yanked into bizarre, elongated orbits, stretching atoms into grotesque, needle-like shapes. It's as if every particle is trapped in an invisible cosmic vise, forced to dance in directions the field dictates, but the real quantum madness lies deeper. Some theories suggest these conditions might freeze space-time itself, locking particles into rigid, crystalline patterns where movement becomes impossible. Not because of temperature, but because the magnetic field's grip is so absolute, it overrides the very fabric of reality. Picture a world where the rules of quantum physics are rewritten by brute magnetic force. Normally, electrons occupy fuzzy probability clouds around an atom's nucleus. But in a magnetar's crust, those clouds get shredded. The field compresses them into thin, cigar-shaped orbitals, aligning every atom like soldiers in formation. This quantum magnetization doesn't just distort atoms, it warps their very chemistry. Bonds between atoms stiffen unnaturally, creating materials harder than diamond yet as brittle as glass. Some models even predict magnetic superconductivity, where electrons pair up not through temperature but through the sheer will of the field, flowing without resistance in a quantum state we've never seen on Earth. Then there's the space-time twist. At certain critical field strengths, theorists speculate that virtual particles, fleeting quantum fluctuations that usually pop in and out of existence, could get pinned in place. Normally, these particles borrow energy from the vacuum to exist briefly before vanishing. But under a magnetar's grip, they might stretch into frozen threads, effectively crystallizing patches of spacetime itself. It's like hitting pause on the quantum foam that underpins reality, a phenomenon so extreme it blurs the line between magnetism and gravity. What's wild is that we might already have evidence. Magnetar flares often release energy in sharp, discrete bursts, clues that their crusts aren't just cracking, but shattering in ways that defy conventional physics. Each quake could be the sound of spacetime itself snapping under magnetic stress, a reminder that in the universe's most extreme laboratories, the rulebook isn't just bent, it's torn to shreds. Cosmic rays aren't just high-energy particles, they're interstellar bullets, screaming through the galaxy at nearly the speed of light. But where do these subatomic projectiles get their ridiculous energy? The answer lies in the wreckage of dead stars, where magnetic chaos turns supernova remnants and pulsar wind nebulae into nature's most powerful particle accelerators. Picture the Crab Nebula's spinning heart, a pulsar whipping its magnetic field into a frenzy, creating a storm of electromagnetic winds. Charged particles caught in this maelstrom don't just drift, they're catapulted along spiraling magnetic field lines, gaining energy with each loop until they're hurled into deep space with enough force to punch through planets. These environments are anything but gentle. When a massive star explodes as a supernova, it doesn't just scatter debris, it shreds its own magnetic field, twisting it into a labyrinth of shockwaves and turbulent plasma. Protons and electrons surfing these chaotic waves get repeatedly kicked by the collapsing and reconnecting fields, like pinballs ricocheting through an invisible obstacle course. Each collision slings them faster, some reaching energies 1,000,000 times more powerful than anything humanity's most advanced accelerators can produce. The result, a relentless hail of cosmic rays, some carrying so much energy they rival a major league fastball, all packed into a single proton. What's wild is how far these particles travel. Trapped by the Milky Way's galaxy-wide magnetic web, they zigzag across space for tens of thousands of years before finally striking Earth's atmosphere. When they do, they trigger cascades of secondary particles, creating air showers detectable by ground-based observatories. But here's the twist: the highest energy cosmic rays are so powerful, their origins remain a mystery. Some might come from supermassive black holes, while others could be the handiwork of hyper-magnetized neutron stars we've yet to discover. The real kicker. We're literally made of this chaos. Many of the heavier elements in our bodies, carbon, oxygen, iron, were forged in supernova, then scattered across the cosmos by these same magnetic accelerators. Every time a cosmic ray streaks through the night sky, it's not just a random event. It's a relic of stellar violence, a fingerprint of magnetism's invisible hand shaping the universe one particle at a time. Every cosmic rule has its exception, and neutron stars are no different. While Magnetars hog the spotlight with their magnetic theatrics, objects like SXP 1062 flip the script entirely. This neutron star, spinning sluggishly in the outskirts of the Small Magellanic Cloud, boasts a magnetic field millions of times weaker than a typical magnetar, so faint it barely registers against the background hum of the universe. It's the cosmic equivalent of a whisper in a hurricane, and that's precisely what makes it so fascinating. The mystery deepens when you realize SXP 1062 shouldn't exist, at least not according to textbook astrophysics. Born from the same fiery supernova that create magnetars, this neutron star is the oddball of its kind, spinning once every 18 minutes while lazily sipping gas from a companion star. Its magnetic field is so lackluster, it barely disrupts the flow of incoming material, allowing the star to feed without the dramatic X-ray flares typical of its more magnetized cousins. Scientists are torn on how such a neutron star could form. One camp argues these anti-magnetars might be elderly magnetars in disguise, objects whose furious magnetic fields have decayed over eons, their once terrifying power now fizzled into near silence. The other theory is far more radical, that these neutron stars were born different, their cores lacking the turbulent dynamos that amplify magnetism in their siblings. Without that internal generator, their fields might never have reached the extremes we associate with magnetars. What's truly bizarre is the range of personalities neutron stars exhibit. Some, like SGR 180620, are volatile tyrants cracking their crusts under magnetic stress. Others, like SXP 1062, are cosmic retirees, content to spin slowly and fade into obscurity. This diversity suggests something fundamental about how neutron stars evolve, or perhaps how little we truly understand about the chaotic conditions inside a collapsing star's core. The wild card in all this, the companion star. SXB-1062 isn't alone. It orbits a massive partner whose stellar winds feed it steady meals of gas. Some researchers wonder if this long-term relationship has dulled the neutron star's magnetic edge, like a once fierce predator domesticated by regular meals. Or maybe the star was simply born into a quieter life, its magnetic blueprint written differently from the start. Whatever the answer, SXB-1062 proves a crucial point. The universe hates simple categories. For every magnetar blasting gamma rays across the cosmos, there's an anti-magnetar sitting quietly in the shadows, reminding us that even the most extreme objects play by their own rules. And somewhere in that contrast lies the key to unlocking neutron stars' deepest secret, if we're willing to listen to the whispers as carefully as the screams. The same invisible forces that light up the cosmos with magnetars and pulsar jets don't just stay in deep space, they reach out and slap us right here on Earth. Take the Carrington event of 1859, when a solar storm so violent it set telegraph offices on fire. Operators watched in horror as sparks leapt from their machines, some even receiving shocks while the northern lights blazed so brightly, people in Cuba mistook them for sunrise. That was just a taste of what the sun can do, a cosmic sneeze compared to the full-blown tantrums we've witnessed elsewhere in the universe. And here's the terrifying part: if a storm like that hit today, it wouldn't just fry telegraph wires. It would cripple satellites, knock out power grids for months, and send global infrastructure spiraling into chaos. Modern society is far more vulnerable than our 19th century ancestors. Picture this: a coronal mass ejection. A billion-ton cloud of magnetized plasma slams into Earth's magnetic field at millions of kilometers per hour. The impact doesn't just create pretty auroras. It induces wild currents in power lines, overwhelming transformers with surges they were never designed to handle. In 2012, a Carrington-level storm missed Earth by just 9 days. Had it hit, estimates suggest blackouts could have lasted years, with damages topping $2 trillion. GPS systems would fail, plunging shipping and aviation into disarray. Banking networks, water pumps, hospitals, all dependent on electronics we've woven into every layer of civilization. Yet for all its destructive potential, a solar superstorm is barely a flicker compared to the magnetic monsters lurking beyond our solar system. The gamma-ray flare from Magnetar SGR-18620 in 2004, for instance, carried quadrillions of times more energy than the Carrington event. If that had happened within 10 light-years of Earth, the radiation alone could have triggered a mass extinction. What's sobering is how little shields us. Earth's magnetosphere is a flimsy umbrella against a hurricane. In 2015, scientists discovered a flaw in our planetary defense. During extreme solar storms, magnetic reconnection can punch holes in the shield, letting radiation pour through like water through a sieve. Satellites in high orbits, they'd be fried in minutes, their circuits zapped by charged particles. The International Space Station's crew would need to retreat to heavily shielded modules or risk lethal doses of radiation. The irony is stark. The same force that guides migratory birds and powers our compasses could, in one violent instant, undo centuries of technological progress. Power grids might take months to repair, but satellites, rebuilding them could take decades, stranding us without weather forecasting, communications, or even basic navigation. Some nations have begun hardening critical infrastructure, but it's a patchwork effort against a threat that doesn't care about borders. Here's the cosmic perspective. Every day, magnetars and black holes unleash storms that make Carrington look like static cling. Our solar system just happens to orbit in a relatively quiet neighborhood for now. As astronomers scan the galaxy for hyperactive stars, we're left with a chilling realization. We're not just observers of these magnetic extremes, we're potential casualties living on a pale blue dot that's one bad cosmic tantrum away from being plunged back into the pre-digital age. The universe doesn't hate us, it doesn't even notice us, and that's what makes its indifference so terrifying. Navigating space isn't just about plotting a course through the void, it's about surviving a gauntlet of invisible magnetic traps. Cosmic rays, those high-energy particles screaming across the galaxy at near light speed, don't travel in straight lines. They're prisoners of the Milky Way's tangled magnetic web, zigzagging wildly as fields twist their paths into chaotic spirals. For future astronauts venturing beyond our solar system, this isn't just a physics curiosity, it's a lethal navigation hazard. Without a way to predict these magnetic minefields, ships could wander blindly into pockets of radiation dense enough to fry electronics or crew in seconds. The problem gets worse near neutron stars and supernova remnants where magnetic chaos reigns. Imagine piloting a spacecraft through a region where fields shift direction every few thousand kilometers, warping like funhouse mirrors under the influence of dead stars. GPS useless, star charts meaningless. Even light from distant stars would bend unpredictably as it passes through these magnetized war zones, rendering traditional celestial navigation hopeless. That's why scientists are racing to map the galaxy's magnetic highways, not with telescopes, but by tracing the very particles that make space so dangerous. Cosmic rays themselves could hold the key. As these particles ricochet off magnetic fields, they leave faint fingerprints, subtle twists in their polarization that reveal the structure of the fields they've traversed. By analyzing these patterns, astronomers are building the first rough magnetic atlas of nearby space. Future starships might deploy sensors to read cosmic rays in real time, using them like sonar pings to detect and avoid magnetic turbulence ahead. Some prototypes already exist. NASA Voyager probes, now in interstellar space, have detected sudden spikes in cosmic ray density at magnetic boundaries no one knew existed. But the real breakthrough could come from pulsars. These ultra-precise cosmic beacons emit radio waves that twist predictably as they pass through magnetic fields. A ship equipped with pulsar receivers could triangulate its position and measure local field strength simultaneously, essentially using dead stars as interstellar lighthouses. The European Space Agency's Gaia mission has already catalogued thousands of pulsars with this exact goal in mind. Yet even with perfect maps, travelers would face one gruesome truth: the galaxy's magnetic skeleton is alive. Supernova shockwaves, black hole jets, and colliding stellar winds constantly reshape these invisible roads. A route safe today might be a death trap tomorrow. That's why some theorists propose an even wilder solution, not avoiding magnetic fields but harnessing them. Just as sailors once rode ocean currents, starships could surf magnetic rivers, letting natural forces guide them while shielding against radiation. The stakes couldn't be higher. Without cracking this magnetic code, humanity might remain forever trapped in our tiny corner of the cosmos, prisoners of forces we're only beginning to understand. But if we succeed, the galaxy's deadliest labyrinths could become its most powerful highways. Beyond the fury of magnetars and the precision of pulsar jets lies a scale of magnetism so vast it defies human intuition. The sprawling megastructures of galaxy clusters. Imagine not a star, not even a single galaxy, but hundreds of them bound together by gravity, swimming in an ocean of superheated plasma. Here, in these cosmic metropolises, magnetic fields don't just exist, they dominate, stretching across tens of millions of light years like invisible spiderwebs woven by the universe itself. Unlike the hyper-concentrated violence of a magnetar, these fields are diffuse, whispering rather than screaming, but their cumulative power is beyond anything a single object could muster. Take the Perseus cluster, a gargantuan assembly of galaxies over 200 million light-years away. Between its members flows an insanely hot plasma, gas heated to hundreds of millions of degrees, so energetic it glows in X-rays. But what's invisible to our telescopes is even more fascinating. magnetic fields tangled and amplified by the relentless churn of galaxies orbiting one another. Like stirring cream into coffee, this motion stretches and twists the fields into a labyrinth of force lines, some so long they could bridge the gap between the Milky Way and Andromeda a dozen times over. The numbers are staggering. While a Magnetars field might pack a quadrillion Gauss into a space smaller than Manhattan, these cluster-wide fields operate at a mere fraction of that strength, perhaps just a few microgauss. But spread across millions of light-years, that weak field stores more energy than trillions of Magnetars combined. It's the difference between a scalpel and a tidal wave. One slices with precision, the other overwhelms with sheer scale. How do such colossal fields form? The recipe starts with chaos. When galaxies collide or merge, their supermassive black holes stir the surrounding plasma like spoons in a cauldron. Turbulence amplifies tiny, seed fields, leftovers from the early universe, into sprawling networks. Over billions of years, these fields grow like cosmic ivy, threading through the entire cluster. Some theories suggest they might even guide the paths of galaxies themselves, like invisible rails steering trains through the night. The proof is in the details. When astronomers study the light from distant quasars shining through these clusters, they notice something strange. The light's polarization twists slightly. That subtle fingerprint reveals the presence of magnetic fields, their gentle grip bending the paths of charged particles along the way. Other clues come from radio telescopes capturing faint synchrotron glow radiation emitted by electrons spiraling along these invisible highways. Yet for all their immensity, these fields aren't static. They're alive, flexing and recoiling as galaxies move, as black holes belch jets, as entire clusters collide in slow-motion car crashes lasting eons. In the Coma cluster, astronomers have spotted magnetic filaments, a thread-like structures glowing in radio waves, evidence of fields tangled so tightly they've become cosmic knots. Untangling them would require energy rivaling a supernova. What's humbling is how these invisible giants shape everything around them. They steer cosmic rays, funneling particles across intergalactic space. They sculpt the plasma between galaxies, determining where it clumps and where it flows. Some even speculate they could influence the growth of the universe's largest structures, sculpting the cosmic web itself. And here's the twist: we're only seeing the tip of the iceberg. Current telescopes barely resolve these fields' faint signatures. Future observatories, like the Square Kilometre Array, promise to unveil their full complexity, mapping magnetic tendrils across the cosmos like cartographers charting uncharted seas. So next time you marvel at a Magnetar's raw power, remember, out in the deep, dark voids between galaxies, magnetism works on a canvas so vast, it makes even the universe's most violent objects seem small. Far beyond our solar system, entire worlds are caught in a cosmic tug of war between gravity and magnetism, and the results are more spectacular than anything Earth could conjure. Picture TRAPPIST-1e, a rocky exoplanet locked in a tight orbit around its dim red star. Unlike Earth, this world doesn't spin freely. One side forever bakes under eternal daylight, while the other languishes in frozen darkness. But the real drama isn't just the temperature extremes, it's the invisible battle unfolding in its skies. Bombarded by stellar winds laced with magnetic fury, TRAPPIST-1e's atmosphere might be sculpted into colossal electric currents, creating auroras so vast they'd drown our northern lights in comparison. The secret lies in the star's relentless magnetic assault. Red dwarfs like TRAPPIST-1's host are notorious for their tantrums, flinging flares and coronal mass ejections with hundreds of times the ferocity of our Sun. For planets orbiting close enough to potentially hold liquid water, that proximity comes at a price. Their atmospheres are sandblasted by charged particles, stripped away unless a magnetic field stands guard. But here's the twist: on a tidally locked world, that field wouldn't act like Earth's symmetrical shield. It'd warp under the star's gravitational grip, potentially funneling stellar winds toward the planet's permanent twilight zone where hot and cold air collide. The result, a celestial light show beyond imagination. Electrons spiraling along these distorted magnetic lines could ignite auroras encircling the entire planet, not just the poles. On Earth, our auroras shimmer in ribbons. On TRAPPIST-1e, they might form a continuous, swirling crown, a ring of fire dancing where day meets night, powered by a star's wrath. Some models even suggest these currents could redistribute heat, potentially creating habitable pockets in otherwise lethal environments. Yet the true spectacle might be hidden. If TRAPPIST-1e has a global ocean beneath its skies, as many suspect, its waters could act like a conductive layer, amplifying magnetic interactions. Picture tides not just of water, but of magnetism itself, sloshing in response to the star's pull. Subsurface currents might generate secondary fields, tangling with the stellar winds to create feedback loops of energy. The auroras we'd see from space could just be the tip of an electromagnetic iceberg with unseen forces churning below. What's eerie is how familiar yet alien this all feels. Earth's magnetic field protects us, but on these worlds, magnetism doesn't just defend. It dominates, shaping climates, carving auroras into permanent landmarks, and maybe even rewriting the rules for where life could arise. As telescopes like James Webb study these exoplanets' atmospheres, they're not just hunting for water or oxygen, they're searching for the fingerprints of magnetic fields in the glow of alien skies. And every flicker of polarized light might whisper the same truth. Magnetism isn't just a feature of the universe, it's a sculptor of worlds. Even the most extreme magnetic fields in the universe don't last forever. Like aging warriors, white dwarfs and neutron stars gradually lose their magnetic vigor over eons, their once terrifying strength fading into cosmic silence. Take a typical white dwarf, the smoldering core of a dead star. Born with a magnetic field thousands of times stronger than Earth's, it might shine fiercely for billions of years. But as it cools, that field slowly decays, its power leaking away like heat from a dying ember. The process isn't fast, it can take longer than the current age of the universe, but it's inevitable. Without the churning plasma of a living star to sustain it, even the mightiest magnetic field will eventually wither. Neutron stars face a similar fate, though their decline plays out differently. A Magnetar's jaw-dropping quadrillion Gauss field isn't just sitting idle. It's working overtime, pumping energy into space through flares and particle winds. Every outburst siphons off a fraction of its strength, like a battery draining with each use. Over millions of years, that steady leak adds up. Some magnetars may fade into quieter pulsars, their magnetic fields dropping by a factor of 100 or more. Others could become near-invisible relics, their fields so weak they barely disturb the interstellar medium around them. But here's the cosmic twist: this decay isn't always smooth. White dwarfs with strong magnetic fields often rotate slower than their non-magnetic counterparts, as if their fields act like brakes, sapping their spin over time. For neutron stars, the story gets even stranger. Some theories suggest their internal superconductors, exotic quantum fluids in their cores, might abruptly switch off after millennia, causing their external magnetic fields to plummet overnight by cosmic standards. Imagine a magnetar going from universe's strongest magnet to a lukewarm pulsar in just a few thousand years, a blink in astronomical terms. The big question looming over all this is whether the universe's magnetic extremes are just a phase. In its youth, the cosmos crackled with the birth of countless magnetars and highly magnetic white dwarfs. But as stars die and their remnants cool, the universe might be slowly demagnetizing. Billions of years from now, will the night sky be a quieter, tamer place, devoid of the magnetic monsters we see today? Or could new phenomena, collisions between neutron stars, the awakening of dormant black holes, reignite magnetic fury on scales we can't yet predict? There's tantalizing evidence that magnetic fields might not fade without a trace. When a white dwarf's field weakens, it doesn't just vanish, it diffuses into space, seeding the interstellar medium with magnetic fingerprints. These scattered fields could become the building blocks for new stars, new planets, even new magnetars in some distant future. The cycle might not be one of simple decay, but of transformation, a cosmic recycling program where today's dying fields become tomorrow's magnetic nurseries. So while individual stars may lose their magnetic might, the universe itself could be playing a longer game, ensuring magnetism in some form endures. The extremes we marvel at today might be temporary, but their legacy could echo across eternity, woven into the fabric of whatever strange objects the far future holds. Humanity's future on Mars might not depend on thicker spacesuits or underground bunkers, but on building an artificial magnetosphere. Unlike Earth, the red planet lacks a global magnetic shield, leaving it vulnerable to solar winds that have stripped away its atmosphere over billions of years. To terraform Mars, we wouldn't just need to warm it up or add oxygen, we'd need to reforge the very barrier that protects our own planet. Scientists have proposed wild solutions, like placing a massive magnetic dipole at Mars' Lagrange point, creating a protective bubble that could deflect solar radiation like an invisible umbrella. It sounds like sci-fi, but the physics is surprisingly straightforward. Recreate what Earth does naturally, just with human-made engineering on a planetary scale. The stakes couldn't be higher. Without a magnetic field, any atmosphere we generate on Mars would slowly erode, vanishing into space just as its original one did. Worse, astronauts would face constant radiation bombardment, not just from the sun, but from galactic cosmic rays, particles so energetic they can tear through DNA. Earth's magnetosphere absorbs or deflects most of this onslaught, but on Mars, the surface is as exposed as an astronaut floating in deep space. An artificial magnetosphere wouldn't just make Mars habitable, it'd make it survivable. The wildest part, we've already seen nature pull off similar feats. Jupiter's moon Ganymede, though tiny compared to Mars, generates its own magnetic field through a molten iron core, proving that even smaller bodies can produce protective bubbles. Meanwhile, exoplanets like TRAPPIST-1e might owe their potential habitability to tidal forces keeping their cores churning, acting as internal dynamos. The lesson is clear: magnetism isn't just a luxury for life, it's a necessity, but here's where the challenge gets real. Earth's magnetic field is generated by a molten outer core spinning at over 1,000 miles per hour. Replicating that on Mars would require unimaginable energy unless we get creative. Some proposals suggest superconducting rings in orbit, creating a magnetic halo around the planet. Others imagine inflatable plasma shields, using ionized gas to mimic a natural magnetosphere. The common thread: these aren't static solutions. They'd need to flex and adapt, just like Earth's field does during solar storms. The irony is delicious. To become multiplanetary, we might need to borrow the oldest trick in Earth's playbook, wrapping our new home in a magnetic embrace. But unlike nature, we wouldn't have billions of years to perfect it. Every second without protection would mean lost atmosphere, increased radiation, and another hurdle for future colonists. Yet if we succeed, the payoff would be more than survival. It'd be proof that humanity can reshape worlds, not just visit them. And somewhere in that achievement, Mars wouldn't just be a destination. It'd be a testament to how far we've come from creatures sheltered by Earth's magnetism to architects of our own cosmic shields. Every magnet you've ever held, from the one stuck to your fridge to the ones powering hospital MRI machines, has two poles, a north and a south. Break it in half and each piece still has both. This duality is so fundamental it feels like a law of nature. But what if it isn't? What if somewhere in the universe's most extreme environments, magnets could exist with just one pole, either a lonely north or an isolated south? These hypothetical particles, called magnetic monopoles, are the ultimate missing puzzle piece in physics. Finding them wouldn't just be a discovery, it'd be a revolution, rewriting textbooks from the ground up. The hunt for monopoles isn't just academic curiosity, it's a quest to solve one of the universe's greatest asymmetries. Electricity has single charges, electrons negative and protons positive. But magnetism always paired. This imbalance has bugged physicists for over a century, ever since Nobel laureate Paul Dirac showed that monopoles could exist without breaking the laws of quantum mechanics. His math suggested something wild. If even one monopole existed anywhere in the cosmos, it would explain why electric charge comes in fixed, discrete amounts. It'd be like finding a cosmic key that suddenly unlocks why the universe quantizes energy at the most fundamental level. Where would these elusive particles hide? The early universe is prime real estate. In the seething chaos just moments after the Big Bang, before the first atoms formed, space might have been threaded with exotic defects in spacetime, cosmic strings, domain walls, and yes, possibly monopoles. These wouldn't be your average fridge magnet variety. A grand unified theory monopole, forged in the universe's first trillionth of a second, could weigh as much as a bacterium despite being subatomic in size. That's a particle denser than a neutron star, carrying enough magnetic charge to power a city if we could harness it. The problem: theory says the expanding universe should have diluted these relics to near zero density. Yet some models hint they might still lurk in the crushing cores of neutron stars or the turbulent remnants of primordial black holes. Imagine a magnetar so dense, its gravity squeezes magnetic field lines until they fracture into monopole-antimonopole pairs, a magnetic version of matter-antimatter creation. Or picture the early cosmos as a supercooled fluid, with monopoles freezing out like ice crystals in slush, preserved in cosmic voids where time barely touches them. Despite decades of searching from ancient lunar rocks to deep underground detectors, no confirmed monopole has surfaced. But absence of evidence isn't evidence of absence. CERN Large Hadron Collider has tuned collisions to energies mimicking the infant universe, hoping to spark a monopole into fleeting existence. Meanwhile, cosmic ray observatories scan the skies for telltale ionized trails that only a massively charged monopole could leave. Even neutron stars are under scrutiny. If these dense corpses captured even a few monopoles during formation, their magnetic fields could reveal subtle anomalies. The stakes, beyond just balancing the equations, monopoles could unlock technologies we can't yet fathom. A stable monopole beam might twist magnetic storage into something exponentially more powerful than today's hard drives. Or they could catalyze proton decay, turning ordinary matter into energy, a potential power source or doomsday weapon, depending on who's holding the keys. But perhaps the most poetic outcome would be rewriting cosmology itself. If monopoles are found, their very existence could prove that the universe underwent phase transitions in its infancy, like water freezing into ice, leaving defects in spacetime's fabric. They'd be relics of a time before time, whispering secrets about how forces like electromagnetism and the nuclear interactions split apart as the cosmos cooled. For now, monopoles remain ghosts in the equations, but in a universe where black holes went from mathematical oddities to front-page news, where gravitational waves are now routine detections, the hunt continues. Because if there's one lesson physics teaches us, it's this: the universe loves symmetry, and somewhere, in the quietest corners of space or the debris of a particle collision, magnetism's missing half might just be waiting to be found. Space isn't silent, it's a symphony of invisible vibrations, and magnetic fields are its most haunting instruments. NASA spacecraft don't just see these forces, they hear them, translating oscillations into eerie soundscapes that reveal secrets no telescope could capture. Take Earth's magnetosphere. When solar winds batter our magnetic shield, they don't hit a wall, they create ripples like fingers dragging across a cosmic drumhead. Probes like Themis and MMS capture these vibrations, shifting them into human hearing range. What comes out? A chorus of whistles, pops, and groans, the soundtrack of our planet's magnetic field straining under the sun's assault. Then there's Saturn, where NASA Cassini spacecraft uncovered something even stranger. The gas giant's magnetic field doesn't just hum, it sings. As plasma spirals along Saturn's field lines, it generates oscillations at ultra-low frequencies, creating a ghostly duet between the planet and its rings. Shifted into audio, it sounds like a theremin caught in a wind tunnel, a pulsating metallic wail that changes pitch with Saturn's seasons. Scientists call it Saturn's roar, and it's proof that even silent-looking planets have magnetic voices. Now crank those frequencies up to magnetar levels. If Saturn's field whispers and Earth's groans, a magnetar's vibrations would be a full-blown cosmic scream, oscillations so intense they'd shred human eardrums if we could hear them. Picture a neutron star's crust cracking under magnetic stress, sending shock waves through surrounding plasma at frequencies 1,000,000 times higher than any musical note. These aren't just sounds, they're tsunamis of compression, twisting space itself. Some magnetars even pulse in X-rays, their surfaces vibrating like struck bells, emitting tones so precise, astronomers use them to measure the star's density. What's wild is how these sounds betray hidden physics. Earth's magnetospheric whistlers trace electrons spiraling along field lines. Saturn's roar reveals jet streams deep in its atmosphere. And a magnetar's hypothetical scream, it might carry clues about quantum fluids sloshing beneath its surface, or space-time itself vibrating under magnetic strain. We're not just listening to space, we're eavesdropping on the universe's most violent backstage mechanics. So next time you see a silent starscape, remember, the cosmos isn't mute. It's a cacophony of magnetic voices, from the delicate hum of planets to the deafening shrieks of dead stars. We just need the right instruments to tune in. What if our universe's magnetic forces are just one setting on a cosmic dial, and somewhere beyond our reality, entire multiverses hum with fundamentally different rules? Imagine a dimension where magnetism isn't just stronger, but the dominant force, shaping atoms into needle-thin filaments and twisting stars into spiral coils. Or another where it barely exists at all, leaving cosmic structures to assemble under gravity's lonely sway. This isn't just sci-fi fantasy, it's a frontier of theoretical physics where the strength of magnetism isn't a fixed law, but a roll of the dice in a vast multiversal casino. Take star formation in a high magnetism universe. Here, fledgling protostars wouldn't just battle gravity, they'd wrestle with magnetic fields so overpowering, gas clouds could fracture like glass under tension. Molecular clouds might stretch into bizarre, ribbon-like structures, their atoms aligned like iron filings around a magnet, planets forming in such a system. Forget spherical worlds, you'd get pancake-flat disks or mile-high spires, their landscapes sculpted by magnetic pressure as much as gravity. Even light would behave strangely, polarized into eerie, swirling patterns by fields woven through the very fabric of space. Now flip the script, a universe where electromagnetism is a mere whisper. Without robust magnetic fields, supernova would explode asymmetrically, their debris spraying chaotically rather than funneling into neat jets. Pulsars might never form, no magnetic braking to slow their rotation, no lighthouse beams to pierce the darkness. Galaxies would lack the magnetic scaffolding that helps channel cosmic rays and organize spiral arms, potentially leading to more fragmented, irregular shapes. Life itself could struggle. Earth's magnetic field shields us from solar radiation, but in this weak magnetism reality, atmospheres might erode faster, leaving surfaces bathed in lethal stellar fury. The wild card, quantum fluctuations in the early moments of cosmic inflation. Some string theory models suggest the fundamental constants, including electromagnetism's strength, could have settled into different values across bubble universes. Our universe's balance might be pure accident, a Goldilocks scenario where magnetism is just strong enough to enable complexity, but not so dominant that it stifles it. For physicists, these hypotheticals aren't just thought experiments, they're stress tests for our understanding of reality. If alternate magnetism strengths produce universes incapable of forming stars or planets, that could explain why our constants are so finely tuned. Or perhaps every possible variation exists in an infinite multiverse, and we simply inhabit one where the numbers allowed our existence. Either way, magnetism isn't just a feature of our cosmos, it might be the signature of something far grander, written across dimensions we can't yet see. Approaching a magnetar isn't just a bad idea, it's suicide by physics. Picture a spacecraft venturing within a few thousand kilometers of one of these magnetic monsters. At first, everything seems normal, then the hull starts groaning, not from gravity. The magnetar's pull is intense but survivable at this range. No, the real killer is the magnetic field, a quadrillion times stronger than Earth. Like an invisible tidal wave, it hits the ship with forces that rewrite the rules of matter. First to go, the electronics. Navigation systems would flicker and die as the field induces currents powerful enough to melt circuits. Even radiation-hardened processors designed to withstand solar flares would fry in nanoseconds as magnetic flux tears electrons from their carefully arranged pathways. Backup systems useless, shielding a joke. The field penetrates everything, turning wiring into fuses and transforming the ship's computers into molten slag. Then comes the structural nightmare. Most spacecraft rely on aluminum or titanium alloys, materials that, under normal conditions, are sturdy and reliable. But in a magnetar's grip, these metals stop behaving like solids. The magnetic field induces eddy currents so violent, the hull would heat to thousands of degrees in seconds, warping like taffy. Rivets would pop, seams would split, and sections of the ship might even liquefy, droplets of molten metal drifting away like surreal, glowing tears. Even the ship's fuel, likely hydrogen or ionized gases, would become a liability, ionized into a superheated plasma that clings to the exterior like a death shroud. But the true horror, what happens to any crew inside? Human bodies are full of charged particles, ions in blood, electrical signals in nerves. A magnetar's field wouldn't just scramble these signals, it would rearrange them. Neurons might fire uncontrollably, triggering seizures or worse. Iron in hemoglobin could align with the field like microscopic compass needles, distorting blood flow. At extreme ranges, the field gradient itself could pull harder on your feet than your head, stretching atoms apart in a grisly imitation of spaghettification near a black hole. Death wouldn't be instant, it would be a slow, gruesome unraveling as the body's basic chemistry is hijacked by forces evolution never prepared it for. And here's the cruel irony, you wouldn't even see it coming. Magnetars emit most of their fury in X-rays and gamma rays, invisible to the human eye. One moment, the crew might be monitoring a seemingly calm star. The next, their atoms are being rewritten by a force they can't perceive, their ship dissolving around them like paper in a furnace. This isn't just hypothetical caution, it's a lesson in cosmic humility. The universe doesn't just kill with black holes or supernova. Sometimes the deadliest things are the ones you can't see, silent, invisible, and utterly merciless. Surviving a magnetar's vicinity isn't about engineering or bravery. It's about knowing that some frontiers, no matter how tantalizing, were never meant to be crossed. Buried inside ancient meteorites lie frozen secrets, locked away in magnetic fields older than the planets themselves. When the solar system was just a swirling disk of dust and gas, tiny grains of magnetized minerals aligned with the infant sun's magnetic field like microscopic compass needles. As these grains clumped together to form asteroids and later meteorites, their magnetic signals got trapped, preserving a snapshot of our cosmic neighborhood's earliest moments. It's like finding a 4.5 billion-year-old recording of the sun's magnetic lullabies etched into stone. Scientists decode these signals using superconducting quantum interference devices, sensors so sensitive they can detect magnetic fields 1 billion times weaker than Earth's. What they've found is astonishing. The young sun's magnetic field wasn't just strong, it was turbulent, flickering like a candle in a storm as it shaped the swirling protoplanetary disk. Some meteorites even hint at fleeting, hyper-localized fields whipped up by planetary embryos colliding, their magnetic fingerprints frozen mid-chaos. These aren't just rocks, they're time machines revealing how magnetism midwifed the birth of worlds. Now zoom out to neutron stars, where an even more extreme version of this preservation plays out. When a massive star collapses into a neutron star, its magnetic field doesn't just get compressed, it gets fossilized into the crust, a crystalline lattice of iron nuclei under pressures that make diamond feel like tissue paper. The star's final moments, its violent death throes, are imprinted in the tangled magnetic patterns now locked beneath its surface. Like tree rings recording centuries of growth, these magnetic strata tell the story of the star's last explosive breaths. Here's the spine-tingling parallel. Just as meteorites preserve the solar system's infancy, neutron star crusts encode their own violent births. Both are cosmic archivists using magnetism to write their histories in a language we're only beginning to translate. The difference scale. Where meteorites capture fields weaker than a fridge magnet, neutron stars trap intensities that twist the rules of physics. Yet the principle is the same, magnetism as time's scribe, etching the universe's most dramatic moments into the fabric of matter itself. The implications are staggering. If we can read these magnetic records, we might finally understand how planetary systems assemble in their infancy, or how stars die in their final moments. It's forensic astronomy, where every mineral grain and every neutron star tremor is a clue waiting to be deciphered. And with each discovery, we're not just studying magnetic fields, we're learning to read the universe's autobiography, written in the quiet persistence of forces that outlast stars. The future of magnetic field research is about to explode into a golden age, thanks to telescopes so advanced, they'll make today's instruments look like child's toys. Leading the charge is the Square Kilometre Array, or SKA, a revolutionary radio telescope network spanning 2 continents. When it comes online in the late 2020s, its thousands of antennas will work in concert to map cosmic magnetism with jaw-dropping precision, revealing magnetic fields in galaxies so distant their light has traveled billions of years to reach us. But the SKA won't just observe these fields, it'll dissect them, measuring their strength, structure, and even their evolution across cosmic time. Imagine tracing the magnetic heartbeat of the universe from its infancy to today, watching as galaxies weave invisible threads of magnetism into the cosmic web. Yet the SKA is just the beginning. Upcoming missions like the European Space Agency's LISA gravitational wave detector might uncover how merging neutron stars twist space-time and magnetic fields in their violent swan songs. Meanwhile, next-generation X-ray telescopes will peer into the hearts of galaxy clusters, where magnetic fields trap plasma hotter than the sun's core. These tools won't just fill gaps in our knowledge, they'll tear open entirely new frontiers. One tantalizing mystery, whether dark matter, that elusive substance outweighing normal matter 5-to-1, interacts with magnetism at all. Some theories suggest dark particles could carry weak magnetic charges, creating shadowy, dark magnetic fields, weaving unseen through the cosmos. If so, their faint imprints might distort the polarized light from ancient quasars, a ghostly signal next-gen observatories are primed to catch. But the biggest questions revolve around magnetic life cycles. We know stars and galaxies are born with magnetic fields, but how do those fields emerge from chaos? Are they stoked by cosmic turbulence like a whirlpool energizing a dynamo? And when galaxies collide, do their magnetic fields merge or tear each other apart, sparking celestial lightning storms? The SKA could catch these processes in action, watching as infant galaxies spin their first magnetic webs or as black holes braid fields into loops light years wide. Then there's the quantum enigma. Lab experiments suggest certain exotic materials can simulate space-time as a spin ice, where magnetic monopoles might emerge fleetingly. If the universe itself behaved this way in its first moments, could relics of that era primordial magnetic defects still lurk in deep space? The answer might lie in subtle twists in the cosmic microwave background, the afterglow of the Big Bang, where next-gen telescopes could spot the fingerprints of these ancient magnetic fossils. What's exhilarating is how much we don't know. Magnetic fields might hold clues to everything from dark energy's acceleration of the universe to the fate of matter in black hole jets. With tools like the SKA, we're not just building better telescopes, we're crafting keys to unlock magnetism's deepest secrets. And somewhere in those answers, we might find that magnetic fields aren't just part of the universe's story. They could be the invisible ink it's written in. From Earth's humble magnetic shield to the galaxy-crushing forces of Magnetars, we've journeyed across 30 astonishing realities where invisible magnetism sculpts the cosmos. Our planet's gentle field, just strong enough to deflect solar death rays, is a flickering candle next to the supernova blast furnace of a neutron star's magnetism. Yet both play the same cosmic game, shaping matter, guiding energy, and rewriting the rules of physics wherever they reign. Think about the scale. Earth's magnetic umbrella protects fragile life, while Jupiter's colossal field turns volcanic moon dust into radiation death belts. The Sun's writhing magnetic loops unleash fury that could fry our technology, while distant magnetars twist atoms into quantum pretzels with fields strong enough to vaporize you from light years away. And between galaxies, magnetic highways stretch millions of light years, funneling cosmic rays and sculpting the universe's largest structures like invisible hands molding clay. Magnetism isn't just a force, it's the universe's silent architect. It determines how stars are born in stellar nurseries, how black holes fire jets across intergalactic space, and perhaps even how the first galaxies assembled in the infant cosmos. Without it, planets might never form, pulsars would lose their lighthouse beams, and the night sky would lack its most spectacular light shows, from auroras to gamma-ray bursts. Here's the beautiful paradox. We've cracked magnetism's basic equations, yet its extremes still baffle us. Why do some neutron stars become magnetars while others fade into magnetic quiet? How do galaxy-scale fields maintain their structure across billions of years? Every discovery peels back another layer, revealing deeper mysteries waiting to be unraveled. So tell us, which magnetic marvel left you awestruck? Was it the thought of a magnetar's crust shattering under magnetic strain, or Jupiter's eternal auroras powered by a moon's volcanic heartbeat? Drop your pick in the comments and keep looking up, because out there, beyond the fridge magnets and compass needles, the universe is conducting a magnetic symphony grander than anything we've yet imagined. The cosmos doesn't just use magnetism, it dances to its tune, and we've only just begun to hear the music.